Hello everyone, my name is Parsa, and this is a video for analytical chemistry for the Chem 100A class at UCSD, but realistically it could be used for anything. The purpose of this video is to develop intuition for what the Gran plot is. For a lot of students entering analytical chemistry, they don't really know how to employ this. It's not a thing or a concept frequently taught in general chemistry, and yet it has a tremendous amount of use when it comes to calculating stuff that a lot of people in general chemistry would use. So in other words, you could also just use this for Gen Chem. But what am I trying to teach here? It's a concept known as the Gran plot. And I'll just write it out really quickly, the Gran plot. And it's effectively just an alternative way to measure or alternative way to figure out the EQ point, equivalence point. And so you could really use this well and employ it for titrations. And also to use it for experiments relating alkalinity of a certain solution. So, in other words, how well its buffer capacity is or how basic it is. And first and foremost, why would I want to use this type of plot as opposed to what a lot of students are traditionally known to do or use in Gen Chem for titrations, especially as the second derivative or the first derivative plot. And the reason is that the first and second derivative isn't super precise. Its precision is kind of finicky. If you don't have a lot of points, for example, in your data, it's not going to be super well for the second and first derivative. It can kind of be all over the place. And it's just because you're calculating or you're trying to describe something with very limited data, and second and first derivatives really need to be smooth curves to kind of get into a proper estimation. And that's really getting too much into calculus, but you don't really have to worry about that in this case. It's just that this method, the Gran plot, is a more precise way compared to the second derivative plot. And so, what is it? That's the big and most important question here. Well, what I can try to do is provide you a proof for describing it, and then from there move on to a more qualitative description of what it is. And so without further ado, let's set a few standards and descriptions of what we need for the proof, and then from there move on to actually solving it, which isn't too rigorous. It's just a little bit of algebra and rearranging some variables, but other than that, it should be pretty straightforward. I'll try my best to explain what every term means and why those terms fit into what they do and why I do my algebraic operations. So first and foremost, the Henderson-Hausbach equation. pH equals pK plus log A minus being the concentration of conjugate base divided by the concentration of your weak acid. Notice how I said weak acid, you can't use it for strong acids. Secondly, your equivalence point. How am I going to define it? Well, I'm going to define it simply as, which is the universal description, as the mole N of your weak acid being equal to your hydroxide, or in other words, your base. I say hydroxide because a frequent titrant is sodium hydroxide for a lot of Gen Chem and analytical chem stuff. Anyway, how is another way, or how can we represent this equation in another way? Well, I'm going to begin by defining a few terms. CO is the concentration, or sorry, the initial concentration of my solution, in particular of my acid, so of HA. Okay. Secondly, V naught. V naught is my initial volume. Cv is the concentration of my titrant, in this case my base, so cons of base. And by the way, you can flip this around for different graphs. Okay, so it doesn't necessarily have to be concentration of base you're talking about. Using the base as a titrant, you could use an acid as a titrant, and everything that I'm doing here will literally just be flipped. Anyway, so you got concentration of base, and then finally Vb, which is your your volume of strong base. Okay, cool. Well, in that case, what am I going to do? I'm going to define HA. HA, remember, can be defined as moles over volume. And more importantly, the way you could describe it is the following way. You could describe it as the concentration, the initial concentration, multiplied by the final concentration, or sorry, by the final, whoa, I am stuttering. The initial concentration multiplied by the initial volume minus your concentration of your base multiplied by the volume of the base, okay? And this will give you your HA moles, the amount of moles you have in HA over a period of like how much titrant you've added. If you divide all that by the total volume, which is just V naught plus VB, right? Because you're adding base, and by adding base, you're adding a little bit of volume to the solution. You got to add these two things together, and you get your total molarity for your acid, for your weak acid. And for your conjugate acid, or sorry, your conjugate base, it's just simply the amount of weak, the amount of strong base you put in there. The reason for that is because HA plus hydroxide in this case will lead to water and also some A minus. And this is going to be the amount that you create. It's actually really just a 1-to-1-to-1 ratio. But you're basically limited for a period of time on how much hydroxide you have until you've fully reached your equivalence point, and then you get limited by the weak acid. Anyway, so your concentration of conjugate base is simply the moles of weak base, or sorry, strong base, divided by your total volume. And so now I'm going to plug that into this equation right here. And so this equals pKa plus log of A minus, the concentration of A minus being Cb Vb over V naught plus Vb divided by this guy right here. And all this is, again, is just a simple substitution of what these two other variables can represent. Your variables being your concentration of conjugate base and your concentration of or of weak acid. I'm going to cross multiply this entire thing. So top goes to bottom, or bottom goes to top, and middle is kind of multiply with one another. But very quickly, this guy and this guy will cancel out. All you have to do is just multiply and see. But for the sake of saving space, I'm just going to do it there. And you're going to get Cb Vb over this guy equal to your pH. Okay, now I'm going to multiply everything by -1. You're going to get negative pH is equal to negative pKa. And I'm going to tell you why I did this -1 thing in a quick second, but hold on. Minus log of Cb Vb over C0 V0, or not Cb Vb. I can also then rewrite this as negative pH is equal to negative pKa plus, and I move the log to the top. These are using logarithm rules. And so plus log, and it'll become a negative exponent, and that means I can flip my interior. So C naught V naught Cb Vb over Cb Vb. Okay, I'm going to raise everything to the power of 10. So 10 to the negative pH is equal to 10 to the negative pKa plus log C naught V naught. Boom. And using logarithm rules, I know that exponent rules, I know if I have two things added together, it's really just me multiplying them together using the same base. So 10 to the negative pH is equal to 10 to the negative pKa times 10 to the log of C naught V naught minus Cb Vb over Cb Vb. Okay, and so what happens here is that we're going to actually continue trying to simplify. And I'm going to keep 10 to the negative pH as is, but I want you to recognize that 10 to the negative pH is just your moles of acid. Okay? And you might be wondering why. Well, remember that pH is equal to negative log base 10 of H plus concentration. I'm sorry, it's not just moles, it's H plus, rather. I misspoke. Anyways, if I were to raise this thing to the -10 or multiply by -1 and then add this and then remove that and then raise to the 10, it would cancel this guy out and it would just give me the mole or the molarity of H plus. And so that's the same thing with pKa because it's almost the same setup. P is a negative log function. And so what I effectively get by retaining this first and foremost is 10 to the negative pH is equal to Ka times, and then these guys cancel out. So I get C naught, V naught, Cb, Vb over Cb, Vb. And from here, what I'm going to do, I'm going to multiply by Vb on both sides of the equation. And so I get this cancel out if I multiply, this cancels out if I multiply by Vb here, and I multiply by Vb here. Vb, by the way, is how much volume, again, you're adding of strong base, or your titrant. And so Vb times 10 to the negative pH is equal to your Ka multiplied by this large quantity of C naught, V naught minus Cb, Vb over Cb. Now we're going to try to just simplify everything, and we're almost done, basically. Vb times 10 to the negative pH is equal to Ka times C, and I'm going to distribute the Ka and also separate this like fraction over Cb minus Ka, Cb, Vb over Cb. So I can cancel out my Cb's because, you have the same value, just again, basic algebra. So finally I get deduced down to this Vb times 10 to the negative pH is equal to Ka, C naught, V naught over Cb minus Ka, Vb. So this is the equation that we're going to kind of use for the start of our explanation for everything. But what do we have here? We have the volume of base that we have added multiplied by basically just the amount of moles of H plus we have. Okay, so not moles rather, but molarity of H plus. We have, again, volume of base. We have Ka, which is a constant value. We have C naught and V naught, which are constant values as well, right? Because they're the initial concentration and the initial volume of our system. Cb, which is also a constant value, Ka here, which is constant, and Vb, which is variable, right? It changes because we're consistently adding Vb throughout our entire solution. And so what I can say here is the following. This value right here, this term, this expression is constant. This is changing consistently. This is constant right here, this Ka, right? Because it's an acid constant, or acid dissociation constant, rather. And Vb is changing as well. And so I want you to think of this as y equals mx plus b. And you might be asking, well, what are these variables each representing? Well, b is a constant, it's your y-intercept, and it's not going to change. And guess what? This entire expression here doesn't change. And so if we create room for ourselves, we can kind of start denoting things as such. And so b is equal to C naught V naught over Cb Ka. And again, all of these values do not change. Our y is equal to Vb times 10 to the negative pH because our pH does change as we add more base, right? It increases, and so does the amount of volume of base that we add. So these two things vary. And you really want to know what this is asking you is basically it's just measuring your change in your mole or your molarity of acid. That's it. Next, by the way, we have our slope. Our slope is just negative Ka, right? Because slope is constant technically. The amount, this is a linear relationship. It's going to be a constant change. And finally, Vb equals x. And so now that we have set all these variables as such, it's time to kind of employ the benefit of using the Gran plot, which is the x-intercept. In other words, VB times 10 to the negative pH equals 0. And if that's the case, 0 equals Ka times CoVO over Cb minus Ka over Vb. If I try to bring my values to one side and try to isolate, I get Ka Vb equal to Ka C naught V naught over Cb. These Kas can cancel out. And I'm going to multiply both sides by Cb. So Vb times Cb equals C naught times V naught at the x-intercept. In other words, where y equals 0, and remember that y is this expression right here. And so what I'm saying here is that the volume of base that I've added multiplied by the concentration of my base is equal to the initial concentration of my acid multiplied by the initial volume of my system. And so what do we define as the equivalence point? We define it as this, which could also be conversely described as CV or C naught V naught equals CB VB. Because again, this is an expression for moles, right? And think about it, molarity M is equal to N over V. M times V is equal to N. And so in that way, we literally have figured out our equivalence point by getting the x-intercept, linearizing the data in this manner right here, right? And boom, you have a way to figure out your equivalence point. Now, how do I actually employ this in like an Excel sheet, which you probably will have to do in an analytical chemistry class? Well, first of all, you are most likely going to have all your VB, right? Because that's you've measured it. It's your ml of titrant added. So not the burette reading, but the ml of titrant added. Okay. So you have VB, and it's just volume of titrant. You're going to have your pH. You're measuring it somehow. Okay. Probably with a pH meter. And all you have to do literally is multiply this guy's quantity or the cells in here by the amount of pH and also have that basically 10 to the power of. And so what you can basically just write is say like the function that you're doing for a cell is equal to VB. So you get all the values in VB and you multiply it by their corresponding pH values by doing 10 to the negative pH. And so you're going to create a set of values here that are 10 to the negative pH times VB, right? And also, in other words, your concentration of acid. And realistically, your data should be somewhat linear, okay? And you're going to compare this, right, your y value, you're going to do it versus your x, and your x is just VB, so the amount of titrant you've added. And what the graph is going to look like, this is more of a qualitative description, something like this. So VB times 10 to the negative pH over VB. And what it really should ideally look like is something that's linear, like this. And it kind of just hits the x-axis, like this. Conversely, it could also be the other way, where it's like this. And it doesn't matter, it's just how your values have assorted themselves. But the idea, though, here, okay, is very important. Think about a titration. Let's say a weak acid titration. This is the qualitative description of it. As I increase the amount of titrant I add, I'm going to reduce the amount of protons that I have because they're going to get neutralized. And so at first, I'm going to start off with a lot of weak acid and or in a higher concentration of H plus right here, right? And because this is where if I go further up, right, this is my 0 mark. And as I go further and further down, right, the amount of H plus that I have gets really, really small. As a matter of fact, it basically approaches 0, right? Because once you titrate something, you don't really have too much protons left. You will have some, okay, to be perfectly honest, you will have some, but it's negligible at a certain point because you're going to go in weak acid, weak base in weak acid, weak base titrations, you're going to go past the 10 to the negative 7 mark. Okay, so these are really, really minuscule numbers. And so again, you're going to go from a lot of acid or a lot of proton concentration, and you're just going to drop it. And that's why this quantity gets super low. It's really because it's a function of the H plus molarity. Okay? And so right here is around the area in which your equivalence point is going to exist. Now, you're not going to get perfect data. Okay? And so you won't see it necessarily hit the x-intercept, but it will get really close. And that's what matters. It's when it gets super close. So you can eyeball it, which I wouldn't recommend. So how to really do this, you can set up and create a curve, and then you can eyeball it and say like, oh, well, that's probably my equivalence point at the ML in which you hit the x-intercept. What you can conversely do, and this is a great opportunity to do it right now if you have data in front of you, is to use the Linus function and figure out what part of your data, when it's linearized over here, has the best linear fit. And so this right here, what I've drawn, is an ideal description of what it's supposed to look like. It's not going to actually look like that. It's going to possibly look something more like that. Okay? That is more towards what your realistic data could look like. And so what you want to do is convert your y values into the VB times 10 to the negative pH, right? Have that plotted versus your regular amount of VB, your volume of titrant added, and then figure out what parts of the upward portion or the downward portion, right? Because it depends on how you're looking at the graph. What points, not the horizontal area, but what points here, right, in the part that's actually above the x-axis, what parts have the best linear fit? And so you're literally going to have to go through a bunch of data points, see which one has the best r squared value, r squared being like the best amount of relationship between x and y. How well can x describe y based off of the fit you have? And so you're going to use that to determine what the best slope can be to describe that line, and then you're going to interpolate the data, or sorry, extrapolate the data, not interpolate, because you could be picking points, or you could be picking a line that is outside of the or creating a line that will basically go past what you typically have, and so it's supposed to be a pretty good approximation of what you have. And so again, use the Linus function, look through all the VB times 10 to the negative pH data, see which section or corresponding areas of VB times 10 to the negative pH relative to the x-axis actually has a greater degree of linearity to it. Use that for your slope, and from there, extrapolate the data by setting what your x-intercept should be, meaning setting the slope and the y-intercept that you get to 0, and you say 0 mx plus b, negative b over m equals x. And the m and the b that you get, I'd like to reiterate again, is going to be from the Linus data that you're going to use to extrapolate. Okay, I cannot emphasize this enough. People will get confused when they see their plot and they're like, why is it not linear? It's not perfect data. What am I going to do next? You use the Linus function, figure out the part of the upward part of the curve that's above the x-axis that has the best degree of linearity. Again, could not stress it enough. But that's all. I hope that helped. I know it was a bit of a long thing, but it's definitely manageable math. Highly recommend writing all these variables down and just going through everything that I wrote again. Um, and here is a larger to scale things so you can pause the video and just look at it. And hopefully you can just try to follow the math through. And with that being said, best of luck and thank you for watching this video. I hope it helped and have a good night.